I find it easier to explain quantum entanglement through a Rubik's Cube. The reason to me is simple. First, this is a dynamic object, so you can see it changing in real time, pretty much as you will expect from quantum entanglement. Second, I think you can think of measuring the center of a Rubik's Cube as a measure of probability because it's constantly moving. And you can see that if you have a Rubik's Cube in your hand, there's certain probability that a color will appear in full or in part. In the center in particular, we're going to use it because there is also the possibility of having positives and negatives. I like to think that the primary colors are positive. So here in the center, you can have a primary color which is blue, red, or yellow. But if you have these three colors and you just look at the opposite, then you will have non-primary colors which I think are negative. So it's orange, white, and green. So they're always at the opposite side of one of the primary colors, due to the disposition of the cube. So yeah, there is probability in quantum measurement. So you know that there's a limited set of options, and you can get one of them by random chance. The distribution is limited, but it's random, and you can only see the spin. You can only define the spin once you measure it. Before that, it's a dynamic object, and we can only know what spin is on a certain time. When you measure it, you take a snapshot, and that's pretty much it. So physicists often say the spin is created at the moment of measurement. Before that, it's not really there. So you can entangle a cube. You can have a mirror image of each other. It works pretty much like this. So you can see that while I'm spinning one of the cubes, the other one is spinning despite me not touching it. And that's pretty much how entanglement works. And the reason we know this is that whenever the spin is measured from one specific axis, so I'm just gonna turn like this, and hopefully the camera can capture the differences in spin. So while this one is negative, the one over there is positive in the same axis. When they measure from a different axis and they say this is positive, they see that the one over there is negative, dynamically changing, while this one, because we know it's a dynamic process. The reason why this happens is unclear. Physicists say these two cubes, the particle and the antiparticle, they act as two halves of the same object, and it's a non-local object. But this is problematic because of the distance, and because we lack an understanding of why this happens. How do they coordinate?